Why do computers exist? Why do we need computers at all? A computer doesn't understand your problem. It doesn't understand your intention. It doesn't know that a number is a number, that a letter is a letter, that an image is an image. And yet computers can simulate entire worlds, render films, translate languages, guide spacecraft, and connect billions of people. That seems almost contradictory. How can something that understands nothing produce behavior that can be so useful and sometimes even look intelligent? To understand why computers exist, we first need to understand what they actually do. Consider something simple. We start with two numbers, 3 and 5. We add them and get 8. Or we start with some text, hello, and transform into hello. Or we start with the lists, 3, 1, 2, and rearrange into 1, 2, 3. These problems look different. Arithmetic, text, sorting, but underneath the same basic thing is happening. We begin with something, we transform it, and we end with something different. That process is computation. But this creates another question. What exactly are we transforming? Numbers? Letters? Images? Sound? What do all these things have in common? They are all forms of information. But what is information? Let's take something extremely simple. The number 65. I can write using decimal digits 6, 5. I can write the same number using words 65. Or I could use Roman numerals LXV. These look completely different, but they can all represent the same thing. The representation changed, but the information didn't. This distinction is important. Information is not tied to one particular physical form. The same idea can be represented by ink on paper, pixels on the screen, patterns of sound. And that raises another question. If a representation can take many forms, where does its meaning coming from? Look at this. What does it mean? At first, we can't really tell. We could interpret this pattern as the binary number 65. But under another convention, the exact same pattern can represent the character A. The bits didn't change. What changed was how we interpreted them. So, meaning isn't magically contained inside the bits themselves. A physical pattern becomes useful because we give it an interpretation. We decide what the different possible states are going to represent. And this gets us closer to understanding computers. A computer doesn't need to know that this pattern means the letter A. It only needs to respond consistently to the physical pattern. The meaning comes from the system we built around it. But if information can be represented using physical states, then at any particular moment the machine must have some particular arrangement of those states. And that brings us to another idea: state. Imagine a very simple system. A value is 3, a light is off, a door is closed. Together these values describe how the system is right now. A computer is also full of states. Numbers stored in memory, values held temporarily inside the processor, the current instruction, pixels waiting to be displayed, and countless other physical conditions. At any moment, all of those states describe the machine as is currently his. But there's a problem. Remaining in the same state accomplishes nothing. If you want the machine to actually do something, the state has to change. So now we need to answer a new question. How do we decide what the next state should be? Suppose our current state is this list: 3, 1, 2. and we want to reach this state 1, 2, 3. Knowing where we are and knowing where we want to end doesn't tell us how to get there. We need rules for transforming one state into another. For example, compare two values. If they are in the wrong order, swap them, then continue. The exact sorting method isn't important here. What matters is that we now have a procedure, a set of rules that tells us how to transform the current state into a new one. That is the basic role of an algorithm. So we now have something very powerful. Information can be represented as states, and algorithms can describe how that state should change. But we created another problem. An algorithm doesn't execute itself. A recipe doesn't cook food. A musical score doesn't produce sound. And an algorithm written on a piece of paper doesn't transform anything by itself. The algorithm is information too. It describes what should happen, but something still has to make it happen. Something has to physically carry out those transformations. And that is where the machine becomes necessary. Now imagine a physical machine that can carry out rules like this. When the machine is in one state, it reacts in a predictable way and changes into another. That new state can then become the starting point for the next transformation. One step can be extremely simple, but connect many simple steps together and the machine can carry out a much more complex process. The machine doesn't need to understand what those states mean. We choose what they represent. We choose the rules. The machine's job is simply to carry out those physical changes reliably. Now we can return to the question we started with. Why do computers exist? Because humans constantly want to transform information. We need to calculate, sort, search, compare, store, retrieve, communicate, simulate, render, predict. We can perform many of these transformations ourselves. But doing them manually can be slow, repetitive, error-prone, or simply impossible at the scale we need. So we build machines that can perform those transformations for us. A computer is a machine that lets us mechanize transformations of information. That's what makes it useful, not because the machine understands what the information means, but because we understand it. We decide what its states represent. We decide which transformations are useful, and we build the system so that physical processes carry them out reliably. How can something abstract be represented inside something physical? That's the problem we'll solve next. If you want to understand how computers really work, from physical states all the way up to software, subscribe to the channel and follow this series.